Okay, so welcome everybody. It's nearly 2 minutes past 3, and I've seen that most of the speakers are already present, and we have a significant number of people in the audience. Welcome back to this second day of this virtual workshop on how to reduce the carbon emissions of concrete by 50%, an ambitious aim. My name is Wolfram Schmidt. I work at the German Federal Institute for Materials Research and Testing in Berlin. Yesterday in the discussion, I already stated that Germans cannot really survive without having rules. So today I'm very happy that as a chairman, I do have the privilege to set the rules, and therefore I would like to give some of these rules in order to allow for a lively discussion, but at the same time for a fair treatment of all the speakers. Therefore, I would really kindly like to request you to abide these rules. And these would be: every speaker has to stick to the scheduled time, which typically is 5 minutes, except for those who were given a slightly longer slot. I will brutally intervene if the scheduled time is running out in order to allow for question and answers afterwards. The exceeded time will be minused from the question and answer time afterwards. You will get remote control, so it's not necessary to ask for the next slide. This will be done by Duff. But if you want, he can also forward the slides if this is required. If you do have questions, please address the speaker you want to address in the chat and give a short information on that question. Maybe the speaker can directly answer on it, but I can also take these questions for the discussion after each talk. After each 5 minutes talk, or 10 minutes or 15 minutes talk, we will have, depending on the time, like 3 minutes for questions and answers. But those speakers who were given 10 minutes or 15 minutes to talk, I assume that they can quite comprehensively elaborate. So I would prefer not to have any questions directly, but rather have the questions raised through the chat. And please also hold back those questions which are very time intensive in the formulation or personal lengthy statements. And also the answers should be very short so that more people can raise questions afterwards. I think this is only fair for everyone. After this session, we will have enough time to elaborate on these questions when the official time has run out. So if we are all very disciplined, this will give us some time for an open, free question session after the talks. Before, at the end of the day, Baudewijn will give a short resume of what was discussed today. And after that, this room will still be opened, as I was informed, so we can still have a relaxed chat afterwards and clarify all the questions that were raised. And now, without much further ado, I would like to come to the first speaker. This is Lars Thrane. I think we haven't seen for quite a while. I'm happy to see you here, even if it's only virtual. And he will talk about priorities from 28 ways to reduce carbon emissions. I was wondering if it's ways or days, but here it's written down ways. So Lars, the stage is yours, the virtual stage.
Yes, thank you very much, and nice to see everyone again. Can you hear me? Yes, super. The slides itself, are they on right now, or? There they are, super. Yes, I can just start by introducing myself. My name is Lars, and I am from the Concrete Center at the Danish Technological Institute. Sorry, just go back one. I'm here to talk a little bit about what's the situation is like in Denmark, especially under the framework of this Danish Sustainable Concrete Initiative, which was launched back in 2019. So please, next slide. It's very short, the next slide. But basically, all of this is in line with we got a new government a few years ago now, and they have a lot of focus on the climate situation, and they have set a goal of Denmark needing to reduce CO2 by 70% in 2030 compared to the level in 1990. And in order to do this, they actually defined what was called 13 climate partnerships. for different industries in order to see how realistic this goal was. So there was actually concrete was part of 2 of these partnerships. One on building and construction. This was a partnership headed by the contractor Årslev, and the other one is a partnership for energy-intensive industry, actually, and that was headed by Aalborg Portland. And Aalborg Portland is the number 1 CO2 emitter in Denmark. So it was only natural for them to be heading this partnership. And as you can see, the graph on the right here, it actually shows a sort of a benchmark values for CO2 in terms of CO2 equivalents per square meter per year, which was defined during these climate partnerships. So it's a value around maybe 10, 11, 12 kilograms of CO2. And the goal is by 2030 then to have it reduced maybe down to 4.5 CO2 equivalents per square meter per year. So it's a very ambitious goal. Next slide, please. Then the concrete initiative, actually this was actually launched before all of this, but it actually aligns then very well with the government's idea here. It was launched by the Danish Concrete Association. Yeah, just please go forward. And the aim here is really to reduce CO2 by 50% compared to 2019 level. And that's actually completely aligned with the government's ambition compared to the 1990 level. The idea is to gather the whole value chain, and currently there's more than 70 members, and it's still increasing. And that's and there is workshops, conferences organized, and one of the very important things in this is also to have partner projects as case studies in order to try out new initiatives and have it implemented in practice in order to ensure that we reach these goals. And one of the fundamentals for this work was really in the beginning to have a roadmap which could describe a path towards this goal. And in order to do this, we had like a dialogue with the whole value chain in order to identify specific initiatives which could be implemented into this roadmap. So please just next slide. Yeah, this is just you can see more about it. It's currently it's on Danish, but this is actually the homepage for all of this about this initiative. The roadmap itself that I will come back to is actually also in English, and you can find it under publications on this webpage. But maybe this will also be translated into English in near future. Next slide. Then what I will talk about is this roadmap then. Launched it was published in 2019, and it describes, just take the next slide, 35 initiatives categorized under different categories. But one of the important things for this roadmap was to actually have a baseline. So we spent actually quite a long time to try and define actually how different types of concrete, how much in volume were used of this in 2019 and the equivalent CO2 of this. So this is actually the baseline, and you can see this categorized into ready-mix concrete, elements, blocks, paving stones, and pipes. And then it's also categorized according to whether or not it's a civil engineering structure or it's small housing applications or larger buildings. So this was the baseline and the fundamentals for actually, take the next slide, for actually trying to have these 35 initiatives and then trying to estimate what would be the time frame for implementation of different initiatives, and also to make a rough estimate on the CO2 reduction potential. And you can see here the different initiatives are categorized under 5 different themes. It's design, planning, and collaboration. It's about requirements. It's about production and execution. it's about circular economy, and it's about process optimization.
Lars, could you hurry up?
Yeah, they have just one slide left. And basically all of these initiatives, 35 initiatives, they are actually all focused on either of these 8 ways of reducing CO2, which is either having greener cement or binders, green concrete, optimized use of concrete, and so forth. So yeah, so this is basically very, very quick overview of what's been going on. And this roadmap is defining the work currently going on in Denmark. Yeah, thank you.
Thank you very much, Lars, for this. I don't see any direct question in the chat. I would ask the audience to better use the chat function for questions and answers, because then we can also do this during the next presentation to respond on more questions. I just ask the audience, is there someone who would like to ask a direct question now? If not, maybe Lars, one question from my side. This seems to be quite a very good initiative, but it's initiated in Denmark. How are you trying to spread this idea and the concept into the world?
Well, the first, you can say more, was actually just to have this roadmap translated into English. That was the first step, and we can now see that it's actually it's been used, I guess, also in Holland now, and we have also talked to the GCCA about it, and but I guess further dissemination of what's going on in Denmark will of course be one of our main goals, and to spread the know-how in that way.
Okay, great. And Mareike Arts, I think, is asking if we can put the link to this roadmap into the chat.
Yes, of course,
so
I can do that right away.
So
yeah,
this way we can already spread this idea.
Yes, of course.
Wider range.
Yeah.
Okay, thank you very much, Lars.
Yes.
We all clap hands. You can see it here. Unfortunately, we cannot hear it at the moment. Everybody is muted. So we directly come to the next speaker without further ado, and this is Professor Kees Kleinman. I was informed he's from Eindhoven University of Technology, by the way, the place where I did my PhD. So I'm looking very much forward to the next presentation, which is entitled, What Does the Structural Sustainability Engineer Need?
Next, I first will show you some project. That's a tunneling project, tunneling master. Next.
Just an information, very short, very sorry to interrupt you, but you can also forward yourself. You should have full control over your presentation.
I'm sorry?
I think you can also flip the slides forward. You should have control over your slides as well.
I will try so. Yes, that's, here are some projects. You saw Calatrava in Milwaukee, that's Milwaukee as well. Here you see a building in Hamburg. Well, it's not working that well. Again, Paris, next. Museum Bonnefante, next. Here you see the design of the architect. Next. That's Gary in Chicago, next. Pudong in Shanghai, next. Beijing, Oma, next. Elb Philharmonie, Hamburg, next. And that's the metro in Amsterdam, next. Well, I show you some typical projects, and most people will know the architect, but who knows the structural engineer? Because the structural engineer, he has to make his schemes, like you see here, for example, for a high-rise building. Next. Or this one, next. Next. And here you see what is the structural engineer designing. How will a structure behave? Will it be linear? Will it be second order? Will it be plastic? or will it, and the real behavior is the red line. And a lot of mistakes are made throughout the world in deciding how to make the construction. Next. So what's the focus of a structural engineer? The focus of a structural engineer is mechanics and mathematics, and he has to deal with strength, stability, and stiffness. Next. And in order to make his calculation, he needs the proper material properties for compression, tension, shear, torsion, modulus of elasticity, quite important. Next. And he has to deal with material behavior, bond stresses, shrinkage, creep, relaxation, environmental aggression, cracking, safety statistics, fire resistance, ductility. Next. Temperature problems, fatigue strengths, freezing, thawing, curing. Next. And then we have a lot of concrete, lightweight, normal, high strengths, ultra high strengths, fiber concrete, self-compacting concrete, pretensioned, post-tensioned, and so on. And considering already that's what the structural engineer is doing, he does his life cycle analysis. He is considered about recycling materials. He is considered about recycled concrete aggregate, but also recycling building elements and reinforcing existing buildings. Next. And now we have the carbon footprint in order to save the world. Next. We are badly in need, like the previous speaker showed us. We need low carbon print cement or less cement or substitutes, not other additives. Yeah, next. And the structural engineers needs all the input of material properties and material behavior for all new materials in such a way that he can use it in the codes that we have now, such as, and here they are again, compression, tension, shear, torsion, etc., dealing with the same things I already mentioned. Next. That's the way the whole world is thinking about the structural engineer as a Calimero in a room making his calculations. It's a complete wrong idea. How it is organized? Well, in Holland and in many other countries, we have a structural engineer for all different things. We have a structural engineer for the design. We have another engineer for constructive cohesion. We have another structural engineer for detailing. We have another engineer for what is it? The control of the detail engineering. We have a coordinator. So the whole design is split up. Next. And how it should be? Well, it should be quite easy. We have a structural engineer dealing with everything. And that's just one person. He knows what he designed and he knows all the in and outputs of the building. Next. And the structural engineer, I'm sure he is ready and he is capable for all aspects regarding the carbon footprints, because he determines the structural dimensions, the steel quality, the concrete quality, the desired strength in time. Next. And the structural engineer is capable to cope with all the aspects regarding the carbon footprint, but he needs the tools to do so. Therefore, invest in research for new concretes now and support pilot experiments. These pilot experiments are, well, the first thing to do to make a better understanding of a low carbon footprint. Next. And then the structural engineer has to realize that he's the best, better than all the rest. Time for questions.
Yes, thank you very much for keeping quite a scheduled time despite quite a high number of slides.
I thought I only had 5 minutes.
No, I mean, I was taking the time that Boudewijn gave me before, so you were allocated a few minutes more, but it's fine, it's perfect. Then we can use this time for questions now and also later. Maybe let me start with a short comment, because I think I pretty much could underpin what you were saying, that structural engineers in the future have to learn much more about everything in a more holistic way. And indeed, they have to become something like superheroes to change everything. There's only one comment I really like to raise, and I apologize for this being a bit provocative, but I think that the structural engineer in the future is not automatically a he, because you always said it's he who has to do that, but I'm pretty sure that the structural engineer in the future will be a he or a she. So I think it's very important to mention that. So, and with this, I would like to open the questions probably.
Okay.
Is there any further question on that? If not, I would, well, I would directly come to the next speaker, and maybe the questions can be continued during the chat functions. I mean, we're all here and we can continue this exchange, and after the session, we will have enough time to discuss that. So thank you very much, Professor Kleinman, for this talk. And I would like to come to the next speaker directly, who is Claudio Subacchi. I think it's the right pronunciation, or Subacchi, I'm not sure, Subacchi probably, from FSC Tech, and he will talk about replacing steel.
Yeah, I'm Claudio Subacchi. You are correct. That is the right pronunciation. Okay, I think you have my slides, I think, or do I have to share them? Here we are. Okay, what we would like to, the speech is about talking a little bit about how reinforcing, how could happen without any kind of steel in concrete. Basically, I think as you can see in the first picture there, I think even if it's a very long time that we know about FRP, are still not get very much traction yet in the concrete structure, mostly because are very different from steel, in the meaning that FRP has a much lower young modulus versus steel, and these generate a little bit of difficulties, because most of the actually structure are designed normally to be steel reinforced, and when you get to the point where you are trying to use FRPs, a lot of problems come up. First of all, because being more elastic, so they stretch more, is more difficult control cracks, in the meaning that you need more material because you have to compensate that lower tensor modulus, and also because up to now they have always been used as a steel replacement, in the meaning that you can find FRP bars that have sizes very close to what you can find about steel. But since they are a composite material, they don't exactly behave as steel is doing, basically, in the meaning that if you have a relatively large section, larger the section you have, and lower is the specific strength. So having very large FRP section is not paying off in the meaning that your specific strength go down, mean that you need to have very large section, and consequently is becoming extremely expensive. Here I'm here to show a little bit what we developed to avoid all those kind of systems. And basically, the first things we came up with is since FRP have relatively low young modulus, the best use as a reinforcement is something used to be stressed to apply a compression to the concrete, not so much as a normal non-stressed reinforcement, basically as a regular reinforcement. And the second step we was trying to develop was to go away from the problems that you have when you are making FRP bars. FRP bars are normally made out of a pultrusion, which is a process, the most used process for do that kind of things. Because how the process work is very difficult to maintain the same load sharing between all the fibers across the section. In the meaning that, for the same reason I was explaining before, when you get a larger section, the specific strength collapse, mostly because that reason, because normally the fiber in the center take less load on the outside of the one on the periphery. So we came up with that system, and the concept is to use the fiber as directly as a roving and apply it to the concrete, to the precast concrete in this case, in tension, which means that you can have a product. We may go to the next step. Next, yeah. So basically, we wrap around the tensile, the area that are in tension, that small roving that is impregnated, and we wrap. Multiple wrap generate multiple the increasing of the load. Doing in that way, we obtain two big things. First things is that we are using a material as a base material that is the first step of the composite production from the fiber standpoint. Basically, is the cheapest material you can find because it has not been already processed, is what you get out from the fiber making process. Second things, because you are applying it in tension, you are almost sure or more sure that all the fibers get the same load sharing, because you don't have something that is subject to different level of pressure from the resin, from the matrix, when it's pultruded. And the third thing is something that is possible to be made in an industrial way. It's, as you can see there, we have a few examples. We first developed that things for pipes, you can see on the left, and basically is consisting in wrapping in tension that composite around a concrete product, that around the pipe, and that is generating a hoop stress, negative hoop stress, basically, enhancing the property of the concrete, and is also generating other kind of needed good behavior, like you can have a water membrane outside, because that composite, when it's curing the resin, is generating also water membrane, and you can actually reduce significantly the CO2 footprint of this, because since you are post-tensioning the product, you can obviously the flexural property go up significantly, and consequently you can reduce significantly the thicknesses for the same amount of load that you can take, more or less the same things that happen between let's say steel reinforced and non-reinforced concrete, basically. We did that on pipe. We are studying that to be applied on a railway sleeper. We did already on slabs, paving slabs, about the size, and we are thinking to do that also on the bottom of beams, girders and so on. The same technology, we develop a system where we use the same technology also on walls. What you see here in the picture is basically a block, a concrete block that has been milled around to generate slots, and those slots they are being filled with that fiber intention. Basically, that block, each single block, has been post-compressed in two directions, and that block is mounted together in a wall. Are mounted together in a wall, generating a wall that has actually a behavior that is completely different from what walls out of that kind of material behave. This wall has a pseudo ductile.
Claudia, short interruption. Sorry, Claudia, but could you try to come to an end within the next minute so that we can stick to the time?
Sure.
Please.
Okay. So basically, it has a completely different behavior. So we go to the next things. Okay, that is an AAC, but more or less it's the same concept. We go next. That is another thing we developed for pre-stressing on a job site casting. Basically, is a pressure activated tendon. Is something that is possible only with composites. Basically, these things is a tendon, an hollow tendon that when it's pressurized is getting longer. That is possible because the ratio between the radial and the axial wrapping of itself, and that permit also multi-directional pre-stressing. You can go in any kind of direction together with many other advantages like in fire resistance building, that things become also an active cooling system for the tensile element. Go next. Here is showing how that things could be done also for reinforce, for move the pre-stressing in various areas, and this is showing that it could be done also as a bidirectional or multi-directional pre-stressing. Next. Same things. This also is showing that the stressing is not actually applied by adhesion between the concrete and the tensioning element, but is actually done by compression of an area, the blue area that you see on the left, top left picture, more or less like what happened on post-tensioning. Go next. And that's it.
Okay, thank you very much, Claudia, for this presentation. I have to apologize that we don't have time for questions right now in order to continue with the schedule, but certainly the chat is working, and I can also observe that in the meantime, it's working quite well. So there have been some questions and answers directly. So please make use of the chat function to get more specific information, and we can take this information also into the discussion later and after the presentations. So the next presenter is Professor John Provis from the University of Sheffield, and he will talk about non-conventional binders. John, you've got 5 minutes. I'm sure it's not a lot for you. You have much more to say, but I'm happy to listen to the next 5 minutes.
Yes, 5 minutes is a good challenge for any academic. We'll see where we get to. So I'm speaking about non-conventional binders. I'm coming very much from a material science and engineering background. So focusing in my research more at the smaller scale, but acknowledging that what we need is at the larger scale. So if I click with a small amount of luck, yes, it moves forward. Okay. So traditional and non-traditional cements, there are many of these. There are cements of widely different capabilities, both including, say, conventional Portland cement systems, other well-known binders, and others that are still being developed and probably still to be developed. There are many of these available. Not a single one of them is a like-for-like one-to-one replacement for Portland cement, nor should it be, because where we're living now, where we are as a cement ecosystem, we're in a monoculture. We're in I use the example of McDonald's. You can go anywhere in the world and buy the same Big Mac. You can go anywhere in the world and buy the same cement. And to be honest, a Big Mac is equally delicious no matter where you get it. Portland cement is equally excellent no matter where you get it. But we need and deserve alternatives. What we need is materials that are fit for purpose. Robust, cheap, reliable, local. There are many types of cements that will fit the bill in this area across these aspects in different scenarios, in different applications. So fitness for purpose is essential. In our toolkit here, and I'm talking in a toolkit approach, again, we have the saying, if you only have a hammer, the whole world starts to look like a nail. So our view of the problem is defined to a large extent by the solutions that we think we have available to us. If we think we have a one-size-fits-all material, we'll end up with a one-size-fits-all solution. If we try to say we need to replace Portland cement by something different, and if we treat that in the singular sense, we will end up with another one-size-fits-all solution. This, to me, is completely the wrong approach. What we need is strength and robustness and versatility through diversity, through selecting the appropriate tools every time around, not ending up like this poor cat in an undersized box in the middle. When I talk about ideas and innovation, does it need to be a new idea? Nothing is really a new idea, in all honesty. People keep writing papers about new cements, innovative cements, novel cements. This has never been done before. And if they dug into some older literature, they'd largely find that it had been. The alkali activated slag is billed as a new cement. This was in large scale use in the US in the late 1890s, patented 1895. Carbonation curing has been done, or US patent I've got here was from 1932. There was a British patent from the 1920s that I couldn't find a screenshot of to throw on this slide, so that isn't there, but there is an earlier patent on carbonation curing as well. Sorel cement, magnesium oxychloride cement, that goes back to the 1860s. Calcium aluminate cement has 100 years of history. Sulfo-aluminate cements have been around since the 60s. There's an old biblical saying, which is, I think, relevant in this case. There is nothing new under the sun, but there are new opportunities for these materials which have had the chance to become established before, but for various reasons have been crowded out of the market or just haven't taken off. So what we need is the right idea to solve each problem. We need flexibility and versatility. We have different environments, different scenarios we're going into, different service environments. Here is just a map of the world with different climate classifications. And if I click, sometimes when I click it moves, there we go, sometimes it doesn't. Differences in economic development levels or GDP per capita. So whether we're looking at developing infrastructure or repairing infrastructure, there's quite a difference in the types of material that will be ideal for a repair or retrofit usage compared to a first off construction usage. Also, differences in availability of byproducts from other heavy industry. Coal ash, blast furnace slag, etc., tend to be concentrated in certain countries, not in others. Differences in geology, differences in mineral resources. A lot of focus and effort has gone into clays, calcined clays, as a way to make innovative cements. And this is important, and it's very, very valuable if you're sitting on or near a clay deposit. Not everybody is. Some parts of the world, there are other mineralogical resources. Some parts have very impure clays, some parts have iron-rich clays, some parts have white clays. very, very wide and diverse range of opportunities posed by geology and mineralogy as well. What can we do with all of this? Where are we taking this, both as researchers and as engineers? Well, we need to ask questions. We need to consider very much more carefully. And in the light of the last talk as well, my first point, does it need to be reinforced? We can say, get more precise on that. Does it need to be reinforced with carbon steel? Some cements that we can look at are absolutely amazing in protecting steel reinforcement. Others are utterly terrible. If you were to put carbon steel into a cement, for example, I would start to question all sorts of things. It can be or should be are questions we need to ask. Just because we can do something doesn't mean we should. Factory production versus on-site production. I mentioned alkali activated materials.
John, could you hurry up a little bit, please? You still have time, but please hurry a little bit.
Yep. I mentioned carbonation curing cements, alkali activated cements need better control of curing conditions under ideal circumstances. You can use alkali activated cements on site, but they're a bit more sensitive to curing. Carbonation curing is ideally suited to factory production. In terms of durability, we don't need to design everything for eternity. We design fit for purpose. If you're pouring a footpath, chances are someone with a digger is going to need to get at the pipe underneath that 5 years from now, rather than 200 years from now. We need predictive capabilities in modeling to be able to understand this. So we need to understand these cements. We need the fundamental research to underpin all of this. Looking forward, we can and must tailor our cement to give the excellent performance we need in each scenario. There are loads of opportunities, but to be able to leverage this, we need high quality data. We need data in the fresh and hardened states. The material needs to be usable and it needs to be effective in service. We need the right applications. We need a robust material because there's a realistic chance our users will be what I would call non-precision. And this is almost unique among engineering materials, the impact that non-precision users can have on cement. And both the material and the application need to be sustainable. We need to take a very holistic view of sustainability, which includes durability, needs to include economic sustainability as well. If something isn't affordable, it's not sustainable. We need the raw materials where and when they are demanded. And I just mentioned as a final point, where we have a specialty application, there are really interesting technical questions and opportunities that can come up from here. So that is, I think, reasonably close to 5 minutes, and I'm happy to answer questions.
Well, I think it was reasonably close to 8 minutes, and so we have completely used the time for.
Close.
It's reasonably close, yeah. I think it's fine because we have that time, but we don't have the time for questions and answers for now. But I can see there are some questions in the chat. So I would prefer to directly switch to the next speaker, who is Yannis Pontikis from Leuven, and he will talk about metal slag recover geopolymer technology project.
Hi, thanks, Wolfram. Is somebody putting my slides? Do I share my slides or what? Okay. Good afternoon also from my side, or from Kai Leuven. This presentation will be speaking about a project. It's called Recover. That was an EIT KIT project. And we can discuss about other things in a different context. In view of the time, I think we should stay a bit focused. Yeah, so what was the Recover about? It was about demonstrating in front of your eyes that we can make sustainable materials. So it was about actually creating 4, which became 6 eventually, mobile units, 20-feet containers. Right, okay. And as raw materials, we would be using bauxite residue, red mud, or copper slag. There is a beauty in that aspect, in the fact that the red mud, 50% iron oxide, is converted thermally into copper slag, which means I'm somehow harmonizing the precursors. And by doing that, I bring together the non-ferrous metallurgy into delivering this new OPC alternative binder, which eventually is going to be transformed into building materials. The project is about to finish. We have, in fact, tomorrow the closing presentation. And this is pretty much what I said. We would be adjusting the residues in front of your eyes and create these new building materials, and there is no trap trick, small letters or magic. The intention also was that these containers will become the seed for industrial symbiosis. So if you would be actually seeing the whole process in front of your eyes, you will be demystifying all this alkyl activation, geopolymer, inorganic polymer terminology, and you will understand that actually you can buy those things from the supermarket and have an efficient process. Am I doing something wrong or somebody? I'm trying to use the buttons, but now I see John. Hi, John.
Duff, can you reshare the screen with us? Maybe it was the wrong button which was clicked.
That's okay. Is my time now running, or do I get an extension all from?
I think we are still good in our schedule, so I think we can make it. So
okay,
just.
But I can speak as the slides come up again. So it had this element of demonstration, okay, and it's also about building trust between the partners and the shareholders of this whole business. And let's go to the next slide. Okay, now I can use it. Cool. All right. Speaking about availability of raw materials, they are widespread in Europe. So we have annual production about 10 million tons. Keep in mind, we have the so-called legacy sites, which means it's a nice word to describe all disposal sites of bauxite residue, more than 100 million tons. And if somebody ever tells me that I don't have enough availability of raw materials, let me just say that we produce annually more than 2 billion tons of iron ore. And when I need in my binders iron ore, I need 50% iron oxide. I can use plenty of bauxite, iron ore, and the likes. So there is enough out there. In fact, the whole formulation is based on the most abundant elements. So please believe me, there is no problem in finding resources, and you can also use non-residues, non-metallurgical waste. Okay, let's go to the next one. Okay, these are things we've done in the meantime. Back in 2015, this is all copper slag, inorganic polymer. 2016, we did this in some of the CRH plants. 2018, the famous staircase. It's an internal jog staircase to heaven. You see the professors are standing up where there is classical concrete. The believers stay in the front, so stay in the center of the staircase. In all of these applications has not been any cement inside. And in fact, we call it, if you press the button, we call it, instead of ordinary Portland cement, we call it extraordinary Leuven cement. All right, let's go to the next slide. This is what I said already. You can see down the chemistry of those binders, abundant elements, more sustainable. We don't go to the 90% lower footprint, but it is still substantially lower. And I call these binders also democratic in the sense that you can find those materials pretty much all over the world. Let's go to the next slide. These were some of the initial designs, and if you click more on the slides, you will see eventually how the design changed from one container to, that was my 5-time slot, to the next design. And please keep on pressing the button. You will see now the real containers, and that was from a matchmaking event we had. We did a matchmaking event 2 days ago at Ireland, at Ogenis. That's the biggest alumina plant in Europe. So we also try to spread the news that this can happen and it can be an alternative reality, and it's about us doing it or not. And coming to the end, where do I want this to take it? I think science is amazing. I'm a professor and I enjoy my research, but at the end of the day, I think we have to demonstrate. So now we have an upscaling facility. We can produce 1 ton a day. And I believe that if we have these containers and actually giving access to people to try to play it, pretty much like Lego blocks, and then you make your own house, then you will build confidence, trust, and actually start developing formulations that are not based on classical cement. So these are centered. where the upscaling facility is now located. That was the end. It was not very smooth. My apologies for that.
No worries, Yanis. I think it's quite a role model behavior that you put your wake-up call to keep the time, and sometimes there's technical problems, so no worries about that. And I think we are safe in this regard, and I would even say we have time for a question if there is a direct question. Otherwise, we can certainly also use the chat function. Is there someone?
I'm checking the chat.
I see some people are moving, but not really raising hands. So thank you very much, Yanis, for this presentation. We can continue to discuss this later. And then I would like to come to the next speaker. And if I take a look at the schedule, it seems that's myself. That was a very funny surprise yesterday when I was asked to give that talk on behalf of my, not on behalf, but let's say in collaboration with my colleague from Nigeria, Kolawole Olonade. Dav, can you share the screen? Kolawole is here in the room, but he cannot present because he's currently traveling. So therefore, maybe you can go back to the first slide. Therefore, I'm going to present this, but it's not a big issue. I will talk about bio-based materials and possible synergistic circular value chains and how rural waste can be converted into urban high-tech construction material. And basically, Kolawole was the one who was supposed to talk about that. Unfortunately, I don't have control over the slides. Kolawole was supposed to be the one to present, but I think I'm a good replacement because on the left side, you can see we are more or less the same, and we have been doing research on sustainable construction materials and the potentials, particularly in Africa, for many, many years. And recently we were also awarded the German African Innovation Incentive Award. So we are doing this pretty close together. Unfortunately, I cannot forward the slide. Yeah. Now let's come to the essence of the talk. And if we take a look at the challenges that the entire world faces in this century, this is urbanization, next, habitat, and also directly next, it's infrastructure, and then it's environment. And what we are talking all about is the sustainability. And if we take a closer look at that, we can identify that concrete plays a major role in all of that. And the reason for that is concrete. There's a huge global demand for concrete, and that certainly makes all of us who deal with concrete responsible for a huge amount of carbon emissions. Concrete, as Karen Scrivener always underpins, is nearly half of everything that the world produces. This is a challenge on the one hand side, but on the other side, it's also a huge potential, because as we use it that much, it can create a tremendous leverage, and it can become the key for the solutions in the future. Next slide, please. But we have to find ways how to use more sustainable cement types. We have to use better concrete in general, and we have to use less cement in this concrete that we're using. And we will identify that Africa plays a major role in this. So this is not going to be changed in the Netherlands or in Germany or in Europe, but those places where the major construction activities will take place will be in Africa. 13 out of the 20, no, sorry, can you go back? 13 out of the most populated cities in 2100 will be on the African continent, led by Lagos, which will have about 88 million inhabitants, so more than the whole country of Germany, just in one city. So there is a huge demand for construction. Next slide, please. And the big potential that African engineers do have in the next 3 decades is that 80% of those urban structures that will be built in 30 years have not yet been built. So then they can be built directly in a sustainable way if we just change the mindset globally. And the good thing about Africa is that the per capita carbon footprint in Africa is below the threshold that is expected to be the threshold to keep the temperatures below the 2 degrees Celsius increase until 2050. So all the other countries come from above. We all have to give up on privileges when Africa can develop a green technology from a very, very good starting position. But this certainly only works. We only have these 30 years time now, and we should really hurry up. We can only try to create synergies between what is required on the African continent and what is available. And Africa has a lot of agriculture and a lot of agricultural growth potential in the future. And at the same time, there's a huge demand for urban construction. So we have to try to develop synergies from this, and there are a lot of potentials. And I will only, can you go to the next slide? Try to elaborate on one example of cassava in Nigeria. Nigeria produces about 20% of the worldwide cassava production. So it's a huge resource. And today cassava is being harvested, it's being peeled, and the inner core of this cassava root is processed further to food. Cassava is also known as manioc or mandioca or yuca or tapioca. And what remains is the waste. And this waste is poisonous to animals, so it cannot be converted into food. It wastes a lot of space. It requires a lot of space when you dump it away. What is typically happening is polluting the environment, it's stinking, there's no further value of that. But what we can do out of that waste, it's really a waste. Can you go to the next? We can convert it to an organic polymer that helps to reduce the water content, thus to tickle out more performance out of concrete. Then it can still be used as a co-fuel for any industrial processes. And what comes out is a pozzolanic ash, which can be used to replace cement in concrete or Portland cement in different cement types. And this way, can you go to the next slide? We can create two non-competing new value chains, one in the construction chemical industry and one in the construction materials industry. And at the same time, we can contribute to energy production. So that's an excellent value chain, which helps the local economy. So next slide, please. And it's not only cassava, it's a lot of different bio-waste which can be used. And here I just did a study how much of each country's total cement processing capacity can be replaced by bio-based ashes. It's not a tremendously high amount, but it's a potential and it's a contributor to reducing the carbon emissions. And it's not only cassava, it's also maize and rice and groundnut, which are particularly interesting in Africa. We've recently built a kiln together with my friend Michael Kome in Ghana, where we process these ashes at the same time create the different interim steps like the organic superplasticizer we produce. Next slide. So this way it's possible not only to deliver farm products to the cities, but also to make virtue out of the waste by producing materials, chemicals, and energy, plus additional precursors for the chemical industry. And this way, this creates new employment perspective in the cities. And in the next step, can you go forward? This urban growth can also significantly contribute to rural development in Africa. And with that, I believe that Africa and the entire global South can become a pioneer for green construction solutions. And with that, finally, I would like to thank you very much for your kind attention. And I think there's still 2 minutes left for questions and answers. Thank you very much. I'm finished with this presentation. I just see a question which is related to Vegemite. So maybe this is a bio-waste, I'm not sure. But I think that's it's another discussion. So I don't see a direct question in the chat. And I also don't see a raised hand. So I would propose we continue with the next speaker. The next speaker is Professor Sofiane Amziane from Université Clermont-Auvergne. And he will talk about bio-beton.
Hello.
Sofiane, are you available?
Yes,
yeah.
I'm ready, yeah. I will try to be in time. You know, I am very, I talk a lot.
I have stopped believing in that, Sofiane, but we will see.
Thank you, Baudouin, for your invitation. Bio-beton is his word. It's not my choice. My title is New Challenges on the Use of Biomass in the Building Materials Construction Industry, but I agree his name, Bio-beton, because I know that he was in France sometimes. Next, please. The actual context, in fact, we use a lot of sand and gravel to make some conventional concrete, and we know all that there is a depletion of sand. Cement, there is a concern with cement due to the responsibility of this material to 5.6% of emission from fossil fuel and decarbonation of calcicline during the fabrication of cement. And for this, we have some good performances in terms of mechanics, with 2050 megapascal conventionally, which is 90% of the ready-mix concrete produced in.
Діма, запиши собі.
Sorry.
Щоб я завтра не забув, запиши собі 8,5.
Please cut your microphone. And also there is 400 kilogram of CO2, around 400 kilogram of CO2 emitted by a ton of, by a cubic meter of concrete. Next, please. I like this illustration of iconic food pyramid. Finally, we are what we eat and we become what we build. This nice sentence is not mine, but I like it because we see that the vegetal have to be at the base of our food to be in a good health. And I think vegetals also have to be at the base of the mixed proportioning to have good material and to build with good the good strategy. Next. And for this, vegetal is good because it is the only, in fact, simplest way to make sequestration of CO2 thanks to photosynthesis. And this photosynthesis is this simple chemical reaction. And with light energy and the CO2, we can produce glucose, which is wood, in fact, and we can sequester 2 tons of CO2 to produce 1 ton of wood. I cannot change. Next. And then we can, in fact, the biobeton, what is the biobeton or bioconcrete? In fact, it's a vegetal concrete made with aggregate made with vegetal and permit the sequestration of CO2 inside the concrete. And we can use some alternative mineral binder made with hydraulic lime, calcic lime, pozzolana, metakaolin, mixed with calcic lime. And this is a simple recipe of bioconcrete. And we obtain a material, very lightweight material, no bearing, unfortunately, with around 0.5, 1 megapascal of strength in compression. Very good insulation material. This is the lambda 0.1 watt per meter per Kelvin, and minus 150, around minus 150, 200 kilogram of CO2 by cubic meter produced. This is the solution, and this is one of the fantastic solutions to change the game in terms of emission of CO2, and not only to divide by 2 the emission of CO2 is to neutralize the problem of CO2 in the production of concrete and material for building construction. Next. What's going on here in France? Because if we need vegetal, we need an industry of vegetal. France, we have chance to be the main producer of industrial vegetal fibers. What I say, what I mean by vegetal industrial vegetal for construction is the fibers like miscanthus, hemp, flax, which is not for food. And we are the #1 in Europe with around 85,000 hectares. And also we can use the non-food part of some vegetals like sunflower, colza, and other corn, for example, and we have the prediction that we will have a huge increase of biomass here in France in building industry, because we will have in 2021 a new standard for insulation of the building, and a new standard based on the CO2 emission during the new construction. And this we will, in fact, we will have a new standard oblige, in fact, the constructor, the building industry to use biomass always in the construction. Next. We have several opportunities. Flax, miscanthus, and hemp are the opportunities in France because we have it. But everywhere in the world, we can use Tifa, for example, in Africa, bamboo, or miscanthus. And we need around 5 or 10 tons of plant aggregate for one house, which means 2 hectares. We have enough everywhere in the world to build a house at a very affordable price, around 500, with 500 euros of biomass, you can build a house. Also, we have an increase of the use of straw bale also in the construction in France. Next, please.
Can you think about 2 minutes maximum left?
Yeah, okay. Also, I have to say that there is the possibility to use a biomass to obtain ashes, aggregate, fiber structures, not only aggregate. Next. And for example, for ashes, we can use maybe with a mix on Portland cement, a mix of ashes at until 20% or 25%. And there is a lot of papers published this years in 2020 and in the last 5 years of the use of ashes, of rice husk, of wood, or of miscanthus. After calcination, there is a pozzolanic reaction of these ashes with cement. Next. And also we can use the fibers to make roofs and walls. Next. And also I would like to talk about the fantastic dynamic of research around bioconcrete. For example, with the mechanical test, bending test, compression test, hydrothermal, acoustical, biodegradability of this type of material. Next.
Conclusions.
Yes, I will conclude. And this, we are going to produce standard because the industry needs standards to have insurance to provide building. Please go to the next slide, because I had 20. Next, not next, the last slide, please. I would conclude to say that we discover in these 20 years that there is a very good alternative with vegetal concrete. Next, with vegetal concrete. And the more important phase will be in the next years, the education. And for example, we start here at Clermont to launch a master engineering on bio-based building materials. Exactly what also I think at Zurich, there is also a master on biomaterials. And this is very important to provide to the industry engineer in this field. Thank you.
Okay, thank you very much, Sofiane. Unfortunately, we don't have time. We have minus 1 minute
no problem.
Time for discussion, but we can shift this to the open discussion afterwards. Because now I would like to come to the last presentation, which is given by Johannes Horvath, and he will talk about first reduced carbon concrete initiative in Austria to foster carbon neutral construction.
Yes, thank you, Mr. Schmidt. Good afternoon from Vienna. My presentation deals about the implementation of reduced carbon concrete in Austria. It's a part of a research project. The first part you get yesterday, the introduction from Mr. Rom. My part is now the implementation. Next slide, please. Reduced carbon concrete are characterized by a minimum content of clinker, or that means minimum content of cement. Our standards, and I assume you know it from the EN 206, they are based from the design concept. We have a minimum of cement content inside and a maximum of allowed water cement ratio, and also additional bundle that we have to use special cements. What we use now here in Austria is, it's okay, you can go to the next slide, what we use here in Austria, and I think it's generally we use in Europe, is a legal basis, a legal technical basis. We also can proceed with such cements, such concretes, and those concretes are called the performance concepts. In Austria, additionally, we also pursue the 5C strategy. So that means clinker, cement, concrete construction, and carbonatization. You see it here on the sketch right above. That means we have to solve or to reduce carbon footprint in all these stages. In clinker, this is the first stage. Maybe you heard it from Professor Hovis. He told you some problems what you have when you go in this direction. Maybe what you can do is, or the biggest deal is maybe this carbon capture, but also to substitute hydration to carbonatization. This is maybe an opportunity for the future, and it's not a big step. So not from an invention for tomorrow, maybe from the day tomorrow. With cement, this is the second C, what we also try to pursue. The problems here with the cement is that we have problems with the availability of constituents, and that's what we say, or what we mean are the quickest step to reduce carbon footprint in concrete structures is to optimize the concrete. Next step, next slide, please. When I go back with one slide to our second C, that means that you have to change the cement. Generally in Europe, we have a clinker factor of about 70%, so we use CEM1 and CEM2 cements. When you go to other cement kinds like CEM3, CEM4, CEM5, or maybe in future CEM6, then you have the problems with the constituents. What we can use is, instead of blast furnace and slag, are maybe some geopolymers, but that means no further research. So maybe this could be only invention for more than 5 years. Next step, Peter. To change, and you heard also from Professor Hovis today in his earlier speech, the way, or to change the clinker, the way from the hydration to carbonatization. Maybe this is an opportunity. The problem behind them is, and you heard it before, that you need new plans, you need new rules, you need new guidelines. And this is also an invention what you can do not for tomorrow, but I think this must be a step for the next 10, 15 years. Next one. So when I come back to our strategy, what we pursue now in Austria, we are promised that this should be a good way to foster and to boost carbon reduced constructions. How we can, or how we start our transformation. So what we need is a performance concept. The problem is how we should start to get a performance concept. Or in the EN 206, you have, there's in general inside it's allowed to use an equivalence performance concept, but nobody knows exactly what is equivalence. And so the basis now in Austria was that we have some guidelines on the basis of such performance concepts, and the important guideline in Austria are for watertight structures. Watertight structure means that we need low temperature and therefore less constrained tensions. To reach such a concrete, we need recepts with or mixed designs with low clinker. Low clinker means on the end low GBP. So this is a misuse from this guideline as a basis. What we have, and the problem what nearly everyone of us in Europe has, is the problem with the carbonatization. So we say the bases are 260 kg per cubic meter for AC1, and you use the K value, and so you can fulfill also XA1. Alternative, you can use also test for hardened concrete. What means when you go a transfer between design concept to the performance concept? You see a sketch below. When we say I want to reach 100% of quality, In Austria, generally, in the design concept, you have a robust buffer in the material, so more than 100%, and that allows also failure on site. When you change this concept in the direction to the performance concept, you reduce the clinker content, you reduce the cement content. So that means you reduce the buffer in the material. What you have to do, you find additional methods to equalize the efficiency from the material on the side of the concrete. That means that we have increased the efforts in the structure, keywords like striking time, maintenance, and maybe also early strange in cold temperature. Next slide, please. Yeah, that's what we build. We find an equivalent, or that's what we have to do, that we must solve an equivalent concept to guarantee durability over minimum 50 years. Next slide, please.
So please consider that there's more or less 1.5 minutes time left. Okay.
Yeah. You see here the testing procedure, what we use, or what we think about, what we use in our research project. I don't go in details in it. Maybe you can also not read it. That's what I want to say, especially that we also test the porosity, because porosity, for our opinion, is an opportunity to test the quality on the construction site. Details for the testing results you get tomorrow from Mr. Hertel. Next slide, please. Yeah, and we are hopefully that summarized say that reduced carbon concrete is not a problem, it is the solution for the future. And I think this research project is a good basis to finish our performance concept on a legal way in this ONR standard. Thank you very much.
Thank you very much also for the final statement. I'm not really sure if it's really not a problem at all, but I think it's a challenge, and we are going to solve this jointly, hand in hand, events like this contribute to that. Certainly, I don't see a direct question in the chat. Is there a question in the audience at the moment? Because otherwise, I noted on my marks here that at 18 minutes past 4, we start with an open question and answer session, and it's now 18 minutes past 4. So we are perfectly in time. It gives us about 10 to 15 minutes now still to have a free discussion about everything that was presented before, or maybe everything that is linked to what was presented before. Before Boudewijn will probably make a kind of a closing statement. As a joke before, I mentioned it could be a blessing. We could see what is going to happen at the end of the day. And before we come to this closing statement with Boudewijn, I would also like to ask everyone, not now, but later, to switch on the camera so that we can have a screenshot with everybody smiling or showing individual moods. But for the moment, I would propose we have an open discussion. And I'm not sure if someone wants to start with that open discussion. And if no one dares opening the discussion, maybe I dare forwarding this task now to Boudewijn, because in the chat you proposed, let me go back, that it's probably an option to match biobeton or bioconcrete, the technology and things that were presented by Sofiane Amzian, with FSC post-tensioning, which was presented by Claudio Subacchi. So Boudewijn, maybe you can elaborate on how you mean this and how your ideas would be to go ahead with this merger.
Well, I don't know if Claudio is there, Sofiane. Basically, I saw at their factory very lightweight materials, and they have an extreme interesting performance on flex strengths, so which is very strange. So it would be for me very logical to combine the two. So I don't know, Claudio, what you think of that, or Rinaldo. You're replacing Claudio, is that correct?
Okay.
Go ahead, Rinaldo.
What I can tell about the flex strength technology, about this, the origin the origin of this technology is because Claudio was the CTO at Okai Petershab, which is the biggest machine for concrete pipe producer. And the concrete pipe were losing market versus plastic and GRP because of their intrinsic limitation for corrosion and everything. And then they developed a technology to improve the life, the market life of the concrete pipe, and this was the origin of this technology. And they understood that by putting together the fiber and the resin and putting them in the direction of the tensile stress, there were a lot of benefits. I can tell also about the application for the railway sleepers. So is a technology that is easily applicable for railway sleepers where because of their corrosion free. The problem of the railway sleeper in concrete now is the corrosion free of the steel due to the crack. And so there are a lot of applications that can new products and on the market and long-lasting life to them. So if you have other points to address the introduction, it would be helpful.
Now, I think also because carbon uptake is also a point of discussion by the Danish. They came up repeatedly on look at the CO2 absorption of concrete in due time. Now you can design the concrete to be, between brackets, bad. That means very porous, taking up the carbon, still having enough strength, of course. So that's why I'm rather excited about this development. That's basically my point. Yeah, and I have lots of comments, but I don't think, Wolfram, that is the idea right now.
Yeah, I think we have, after the session, I think this room will still be open and we can continue until the night. Maybe if someone has a bottle of wine next to its office desk, that would be a good opportunity. But I think one aspect certainly which has to be considered is the separation of the different materials at the end of the day when everything has to be recycled and so on. So there are a lot of questions related to that. I saw one question from Danilo Hadajczuk related to the bioconcrete and about the quality parameters of the incoming raw materials, where that's certainly an issue, but we also have to invest a lot in cement production to homogenize something simple like calcium carbonate. There are always there's always a huge effort to homogenize it, and certainly this would also be required if you have some bio-based ashes. And maybe you even have to do something like an ash blend of different bio-based source, and some really skilled people have to put these oxides together in the right way, depending on the time of the harvest and the soil quality and so on. That would be very challenging. And I also believe that maybe this is not a technology that predominantly has to be applied in a cement production, but rather in a concrete production, so that the bio-wastes can stay within the region and they can be converted directly to farmers and be delivered to a concrete processing plant, so that the concrete producers purchase the normal ordinary Portland cement and then blend it in their concrete construction site. They have a much better control of the quality of the ashes. So I think there are ways, we just have to think about different ways. But I think this local production aspect is interesting because of the new value chains and the livelihood potentials, particularly in Africa and also South America. But one thing that was addressed before, you addressed the Danish people, and maybe I would like to raise another question related to both to Lars and also to Johannes, who opened and who closed the session. Basically, I'm always a little bit struggling with policies. Whenever there's a new policy, a new regulation, it requires a lot more bureaucracy. and it also requires much more understanding of those people who afterwards have to deal with these things. And as mentioned in the last presentation, no one really applies performance-based concept because no one really knows how to do that. So I really appreciate that this is brought forward. But certainly, how do you think Denmark and also Austria and other countries can tackle this challenge of being simple enough for the users to apply it, and also being complicated enough to cater for the challenges that lie ahead? And is it probably necessary also to delete some old standards to the benefit of new regulations and policies?
And really, when I start, yeah, it's a good question. But I think it's not possible to live without standards. Yeah, I think in general we have too much, that's quite right. But to find confidence between all partners in a business, it's, for my opinion, or for our opinion, constraint necessary to offer some guidelines.
Yeah,
the problem behind all them that our design concept, or generally our standards, are based on experience. Yeah, we have a lot of experience with this design concept, and to go away from a design concept in a direction to the performance concept, so you have new approaches. It's not easy to find equal between performance and the design, and that is the challenge. And of course, the EN 206 is not harmonized, and that is a problem. So every country can do their own rules, and maybe, I don't know if it is necessary to do everyone their own, but maybe we can work together like our COVID-19 virus, and then we get maybe earlier a confident standardization. Yeah, but I think, yes, it is necessary to have such a guideline.
Yeah,
maybe Lars can, because he was also addressed. Maybe Lars can.
Oh, sorry.
Respond.
Yeah, I can just add a few. Of course, I think one of the ways to actually change regulation is definitely also by proving the concept, and then we have actually tried quite a lot to go together with the whole value chain in projects to actually have a full-scale demonstration where we try out these concepts. For instance, going together with the Danish Road Directorate to build bridges where we actually try out a performance-based design procedure where requirements on properties and not according to the normal regulations on mixed composition and so on. So I guess also through demonstration we can actually push the normal way of doing things.
I think that was also what was mentioned by the second presenter. I think this demonstration is really something we require, and we also require more funding for this kind of things. Instead of putting funding more into all kinds of policies and so on, I think demonstrators are really one of the keys. But unfortunately, the time is running out now, and Boudewijn, you're already hot for the ongoing discussion. But this room will still be open, so we can still continue to discuss. For the moment, I would propose everybody switch on the camera so that we can take a few screenshots, and after that, Boudewijn will have a kind of closing statement. But maybe everybody can quickly switch on the camera, show us the most beautiful smile that is possible for a few minutes. And then, Daf, I think you take a screenshot, right? So should we all smile or wave hands, or what are we going to do?
I cannot smile that long, okay?
Try it, Boudewijn.
So, okay, Daf, you did your thing on both sides. We have two screens, huh? So, okay.
Okay, so then I would say, Boudewijn, you continue with the last statement before we have a completely free discussion. Without rules, it will be Wild West.
Daf, can you show my very short presentation, which makes it easier so that I don't lose. This is the present economy, okay? The value chain from the client, architect, structural engineer, contractor, subcontractor, supplier, the sub-supplier, okay? The cement and aggregate producer. And what happened? The cement and aggregate influence is I think a little overdone. So we have normally what I learned is that it is the customer who decides what quality is, and he has the money. And so what happened is that the standards have been written by the sub-supplier. And Ian towards, okay, go on, next. They have made lots of money where they have all the influence on the lobby forces, the sponsoring. Next slide, please. This is where we have to get to. And that's the construction ecosystem. It is the client with the money who decides, and he of course, he does not understand the water-binder ratio, and he doesn't understand why in Germany it is 0.92, while in England it is 0.40, with the same mix design. So this is pseudo technology. I know I'm charging, but Wolfram knows me a little bit, he can temper me sometime. But the designer is material neutral. And he should say, I'm using wood, concrete, steel, or whatever, okay? And he should understand what's going on. But he does not get the information he needs right now. He only gets 28 days underwater treatment by 20 degrees. And then I ask, are you putting the building also 28 days underwater before you use it? So we really have to shake up the system and go and become adult on this. So of course we have the knowledge transfer, education, and the science, and they all have their shortcomings and their strengths and so on. But the supplier should supply what the designer says he should get. Okay, next please. We have a system. We use this. We said, you do not need to have standards. If you want to do something correct, we will talk about that tomorrow, how we did the geopolymer the pathway under the railroads of ProRail, not using any Portland cement in it. So this is basically the system I discovered in 2008, and I said, this is it. You know, you go and you look at the verification possibilities, become credible in what you say, okay? And that's all. The standards, I personally made the biggest progress with refractory concrete, where there were no standards on the composition of the material. If we decide to have micronized dog shit, or horse shit is easier to get probably, to put in the concrete, because I am responsible for the final product. Where would we be if the steel industry would dictate how the car should be designed? Okay, so we have to grow up, and this is not against the cement industry. It is from the cement industry has only a profit if they have intelligent customers. And right now, being kept dumb is not the idea. Next, please. Okay, this is a famous formula. You have a new technology in an old organization. Next. And what you get is an expensive old organization. So technological innovation without system and process innovation is pure waste. Okay, so my call is for performance-based standards. We should agree on testing procedures. We can use water powder ratio for design of the mix. And what these powders are, they should be responsible powders. And this gives you a guideline. I totally agree. People do not want to let go of the EN 206 because they need guidelines. Let's give them guidelines, but let's evolve these guidelines because they are outdated. If we have water binder ratios in the UK of 0.40, the same mix, 0.40, in the Netherlands 0.45, in France 0.66, in Germany 0.92. And if you say what you mixed in it, I am mixing in it, I all of a sudden have a water binder ratio of 0.36. So this is pseudo technology. Let's get rid of it and let's replace it with something serious. That is basically my thing. Now, honestly, we have another hour. I would love to have Klaus and Kees Kleinman discuss more about the experience with the structural engineers, because they are going to be the key profession to change things. And the other thing is fantastic. What I saw, what Yanis has been doing with micro industry. Those containers. They are the future, because some community can start with something. Okay, we can. This is a full-scale factory for somewhere in Africa. If they because in Africa they do not have. They are not stuck with the European crazy standards. So let's all work together on give the proper guidelines. Everybody needs it. So again, well, many of you know me, that I'm getting very excited about injustice in this whole system.
So Boudewijn, thank you very much for this final talk and statement. And yeah.
Well, by the way, this is only the beginning of the context we have here, please.
Yeah, I think it's necessary to share the slides. There was a request whether it's possible to share the slides. So I guess that Boudewijn, you can make it possible to if you can make it available, provided the authors agree to that, certainly. Something you said, maybe to close this, I mean, we are already 7 minutes behind schedule. I was expecting 5 minutes. I apologize for this, but I would like to say thank you to all the speakers to basically entirely keep the time, and also for the discussion that took place. And